Today we're going to talk about the general inclusion-exclusion formula and discuss why it should be true, why this general formula that applies to the version we're going to talk about, the intersection of the complements of n sets, and talking about how many elements are in this intersection of the complements. We're going to talk about why this formula holds, no matter how many sets we have. So what does the formula say? It says, if we have a bunch of sets A1 through AN, and all of these sets are going to be subsets of some universe U. So I'll draw the picture here, where we have a universe U consisting of all things that we're interested in talking about. And then inside that universe we have sets A1, A2, A3. And I'm just drawing the pictures if there are 3 sets, but in general you could have any number of sets, 17 sets, 1,000,006 sets, it doesn't matter. And we want to count the size of A1 prime, A2 prime, up to AN prime. What does that look like? Well, A1 prime is the set of everything that's not in A1. A2 prime, the set of everything that's not in A2. A3 prime, the set of everything not in A3, etc. And the intersection of all those means the set of all things that are not in A1 and at the same time not in A2, not in A3, etc. That will consist of exactly this region that's in our universe U, but outside of all of the A's. And you'll remember that by De Morgan's law, that's the same thing as the size of the set U minus, or let me write that a different way. We don't want to talk about set differences now. That's the set A1 union A2 union up to AN, and we take the complement of all that. So the complement of the unions is the same as the intersection of the complements, and that's this set of everything outside of all of the A's. Now, what does our inclusion-exclusion formula say? It says it can be counted by taking S0 minus S1 plus S2 minus S3, etc., all the way until we get to Sn. And I say plus or minus here. It'll be a plus if n is even, a minus if n is odd. And what are the S's? Well, S0 is just the size of the set U, so the size of our universe. S1 is the size of A1 plus the size of A2 up to the size of AN. We can think of this as the sizes of the sets added together, taken one at a time. So there are going to be n terms. Notice here there's just one term. S2 will be the sizes of the sets taken 2 at a time, and we're talking about intersections. So we're looking at the intersection A1, A2, plus the intersection A1, A3, plus all of the other intersections of pairs of sets. How many terms will there be in S2? There'll be exactly n choose 2 terms. And now let's write this down. S0 has just one term. I'm going to write that as n choose 0 terms. That's one term. S1 has n terms. That's n choose 1. And then we keep going. Any S sub k is just the set, the sum of the sizes of the set intersections of the sets taken k at a time. One term would look like A1, A2 through A sub k. But there would be a whole bunch of different ways to take intersections k at a time. I won't write those all down. There'll be exactly n choose k such terms. And of course Sn has just one term. That's the size of A1, A2 up to AN, that intersection, no other terms. There'll be n choose n terms, which is just one. So we take this first number, S0, minus S1 plus S2 minus S3 plus S4, all the way up to plus or minus S sub n, and we get the size of the desired set. We include everything to begin with, then we exclude S1, we include S2, back and forth, and in the end we get exactly the size of the set we're interested in. This intersection of A1 prime, A2 prime through AN prime. Why in the world should this give us exactly the right answer? Well, imagine we have an element X that could be anywhere in our universe. If we want to count the number of things in this shaded region, then if X is in that shaded region, it should be counted once in this sum. If X is not in the shaded region, meaning in any of the A's, it should be counted a net total of 0 times, because we only want to count once for every element outside of all the A's. So let's start by just asking all the different places X could be. If X is in 0 of the A's, by which I mean it's in none of the A's, it's outside all of the A's, how many times is it counted? Well, in this formula here, S0 minus S1 plus S2, etc., X is counted in S0 because every element of U is counted in S0. But if X is not in any of the A's, it's not counted in S1, S2, S3, all the way up to Sn. It's not counted in any of those, so it's counted a net total of 1 time, which is good because we wanted it. I'll put a check here. We wanted it to be counted 1 time. It's what's supposed to be counted, anything outside of all the A's. What if X is in exactly 1 of the A's? So for example, this one that I've shown here, I'm going to put X here. X is in A3, but it's not in any of the other A's. Then how many times is it counted in this formula? Well, it's counted once in S0 when we take the size of the entire universe. X is in there, so it counts for 1. It's counted exactly once in S1 because it's in the set A3. That'll give me a +1 there from that element X, but it's not in any of the others. And so we get +1 from S0, and we're subtracting the 1 from S1. And then I claim that such an X is not counted in any of the other S2, S3 up to Sn because it's not in any pairs of sets. It's only in A3. It's not in any intersection of 2 or more of the sets. So I'll say it's counted a total of 1 from S0 minus 1, which is 0 times. And that's good, because anything that's in one of the sets shouldn't be counted. Only the things in this shaded area should be counted. So it should be counted a net total of 0 times. Let's look what happens if X is in exactly 2 of the A's. How many times is it counted? Well, it's counted once in S0, because everything is. It's counted twice in S1 because it's in 2 of the A's. Just say, for example, it's in A1 and A2, but it doesn't matter which 2. It's counted exactly 2, and we're subtracting that. So it's counted once in S0. We're subtracting a net total of 2 from S1. But now if it's in exactly 2 of the A's, say A1, A2, it will count once in A1 intersect A2. But it won't be in any other intersection of a pair of sets because those are the only 2 A's that it's in. And that will give me a net total of 0 times. And that's good. That would correspond to an element here that's in exactly 2 of the sets. We're counting it a net total of 0 times with this formula, which is the correct number of times we should be counting it. But what if X is in exactly 3 of the A's? Well, how many times is it counted? It's counted once in S0. It's counted 3 times in S1, and we're subtracting that. How many times is it counted in S2? Well, if our element is in exactly 3 of the A's, like this one here, there are 3 choose 2 or 3 different pairs of sets that element is in. And so it's counted 3 times in S2. And we're adding that in. How many times is it counted in S3? Well, S3 will contain exactly one term that has those three A's in it that the element is in. So we're going to have it counted once in S3, and that gets subtracted, and we get a net total of 0 times, which is correct. Anything in any of the A's shouldn't be counted in the end in this formula. Now here you might see a pattern: 1 minus 1, 1 minus 2 minus 1, 1 minus 3 plus 3. I'm sorry, that should be 1 minus 2 plus 1. 1 minus 3 plus 3 minus 1. You should see something, especially if you start with that 1 and put that up here. You'd have 1, 1 minus 1, 1 minus 2 plus 1, 1 minus 3 plus 3 minus 1. Kind of looks like Pascal's triangle. And that's not just a coincidence. What if x is in exactly k of the A's? Here, k could be any number that, let's say, is greater than or equal to 1 and up to n. Well, how many times is it counted? Well, it's counted once in S naught, and I'm going to call that 1 instead of writing it as 1. Well, I'll write it as 1, and then I'll put below that k choose 0, which is equal to 1. How many times is it counted in S1? Well, if x is in k of the A's, it'll be counted k times. It'll be in k of these terms. So we're going to subtract k. That k we can think of as k choose 1. How many terms in S2 will the element x be in? Well, there are n choose 2 terms in S2, but how many of them will contain, how many of these intersections in the terms in S2 will contain x? Well, x is in k of the A's. That means it's in k choose 2 pairs. So we're adding in k choose 2. And then we're going to keep going. How many terms in S3 would x be in? Well, I'm going to subtract because S3 has a minus sign there. It'll be in exactly k choose 3 terms. How many terms from S4? It'll be exactly k choose 4 of those terms because the element x is in k of the A's. S4 consists of the sizes of the intersections of those A's, 4 at a time. K choose 4 is the number of ways we can pick 4 of those k sets that x is in. And then we keep going, alternating signs, up until we get to a plus or minus k choose k. After that, x will be in 0 terms, but for larger numbers of intersections because it's only in k of the A's. Now, this expression should look familiar. These terms look like the entries from Pascal's triangle, but we alternate the signs. So this is what we call an alternating sum of the elements in a row of Pascal's triangle. And one thing we showed earlier in the quarter is that this sum is 0. So I claim this sum is 0. How did we show it? Well, it was very straightforward using the binomial theorem. Using the binomial theorem, if you look at the number 1 plus the number -1 as our binomial expression, raise that to the kth power, what does the binomial theorem tell us about the expansion? Well, I claim it's exactly equal to this. You have k choose 0 times 1 to the k times the -1 to the 0th, plus k choose 1 times 1 to the k minus 1 times -1 to the first power. That gives us the minus sign. And then we'd have k choose 2 times 1 to the k minus 2 times -1 to the second power. So it becomes a plus again. And we keep going, alternating the signs, plus, minus, all the way till we get to the end. And since that's just 1 plus -1 to the kth power, that has to be 0. That's 0 to the kth power. That tells us the alternating sum in any row of Pascal's triangle is exactly 0. And that tells us if x is in any number of the sets from 1 to n, it will be counted 0 times in this formula on the right side of this equation. And that's the correct number of times it should be counted. Any element x that's not in any of the A's will be counted once. every other one will be counted 0 times. That tells us we've got an accurate count of the size of this set. That gives us the inclusion-exclusion formula, which I'll write again like this.